Okay, so now imagine that you've got, let's imagine that these are loudspeakers. This is loudspeaker A and this is loudspeaker B. And I will do this, we'll do this demonstration, right? And that these are our little waves heading out from that speaker. Maybe these are the compressions, and in between are the expansions or the rarefactions, as we say, right? If you consider one little spot like this, right? Notice that this spot right there is 1, 2, 3 wavelengths from this guy, and then it's 1, 2, 3, 4 wavelengths from there. The difference in distance is one whole wavelength, right? So that'll be constructive interference. You'll have these spots here that are constructive. By the way, it's also constructive interference where trough meets trough, like that. Okay. Now let me just show you this. I got to show you this. Okay. This thing shows you this. So I'm going to turn these speakers on. Actually, let me turn this simulation on. We'll turn these speakers on. Notice that there's places here like this, okay, like right here, where there's a lot of sound energy, and there's places here where there's not so much. Let me just show you this. We can actually measure this. Watch. Put this guy here. We'll put this probe right there. Notice that the sound energy there's quite a lot of it, right? If I put the thing right there, this is a place where we'd hear anti-sound. Isn't that fun? And if you move it around, if you kind of move around in this space, you're going to have places where there's not much sound and places where there's a lot of sound, okay? And that's what we're talking about, is the interference patterns. And I'll show you how to solve these problems, okay? I think I'll pause that, okay? By the way, you can do the same thing with light, which is a dramatic evidence that light acts like a wave, okay? And what happens is you shine the light on, it has to be monochromatic, coherent light. Generally, we get it from lasers, right? It has to shine on these little slits. The waves will diffract out from that. That just means they spread out. And when they overlap on the screen, you'll get that same interference pattern, which is super cool. I'll show you this. Okay. But anyway, this is the general rule, right? If it's an integer number of wavelengths, it's constructive. If it's a remainder of a half, it's destructive. So these step by step, this is what you do, right? Calculate the wavelength if you haven't. Probably you'll use V as F lambda, right? Figure out the difference in distance. That's just L1 minus L2, right? So if let's say you're speaker A, speaker B, right? And you're here. This is L1 and maybe this is L2, right? And then figure out how many wavelengths it is. By the way, that's like the wave number, okay? How do you do that? That's just this divided by lambda. And that'll give you a number, 1 wavelength, 2 wavelengths, 3 wavelengths, right? If it's something 0.0, it's constructive. If it's something 0.5, it's destructive. If it's something 0.1, it's mostly constructive. That's kind of like being mostly dead, right? If it's 0.25, that's like a moral dilemma, okay? Let's solve one of these problems, a couple of these problems. Okay, here it is. In air where the speed of sound is 350 meters per second, 2 loudspeakers produce a frequency of 700 hertz. Okay, so let's find the wavelength. The wavelength is the velocity over the frequency. So it's 350 meters per second divided by 700 hertz. And that is, without using my calculator, 0.50. How many sig figs do we have? I guess here, let's put a decimal point there. Then we have 2, right? Meters. That's a wavelength, right? Okay. So let's solve problem B here. If we are 3.21 from the left speaker and 1.22 from the right, is it loud or soft? Well, let's figure out the difference in distance. So 3.21 minus 1.22. 3.21 minus 1.22 is 1.99. And then I'm going to divide that. That's meters, right? I'm going to divide that by 0.500 meters because that's my wavelength, right? So L1 minus L2 divided by the wavelength. So divided by 0.5, and I get 3.98. Right? So what that means is it's almost 4.0. So this is going to be constructive interference. It's going to be loud. Okay? We happen to find a place that's like this, right? Or like here. Okay? We're 1.22 from this one, and I forget 2.21 or something from this one. Okay? That's what's going on. All right. Now let's do part C, right? If we're 4.65 and 5.4, right? So we'll just subtract 5.4 minus 4.65. 5.4 minus 4.65 is 0.75. And then I'm going to divide that by the wavelength. To figure out how many wavelengths, I got to figure out how many wavelengths it is, right? So divided by 0.5, and I get that it's 1.5 wavelengths exactly, right? So that's going to be, destructive. Okay, so it's going to be a situation like this, where we are maybe here, right? I don't know. Okay, and it's going to be, whoops, low amplitude. Is that low amplitude? It's going to be here. It's going to be like that spot right there. Very low amplitude. You can see the pressure right there. Okay. So anyway, the steps are find the wavelength, if they don't give you the wavelength, right? Step 2, figure out the difference in distance, right? Step 3, figure out how many waves that is. Just divide by lambda, right? And then just look at it. If it's close to something 0.0, it's constructive. If it's something close to something 0.5, it's destructive interference. Okay.